Section 4.3 is titled Greatest Common Divisor and Least Common Multiple. And really a continuation of the things we've been looking at in the previous sections about divisors and multiples. So the first one we're going to talk about is the greatest common divisor. It's also called the greatest common factor. So if you hear me say that, that's what I'm referring to, same thing. This is the greatest whole number that divides all the numbers in your set. Please recognize it's still a divisor. So this is still a number that's smaller than the numbers you're already working with. Greatest common divisors are small numbers. They're just the biggest of the small things, right? It's like the tallest hobbit or something like that, okay? They're still small things. Relatively prime, we've actually encountered relatively prime items before. Relatively prime means that you have two or more numbers whose greatest common divisor is 1. In other words, they have nothing in common. So where have we seen that before?
We have two factors that can prove that they're divisible by.
Yeah, right. Back when we did the divisibility rule for 6, and we said the reason the divisibility for 6 rule works is because 2 and 3 have nothing in common. So we would actually have called 2 and 3 relatively prime. And we had lots of other examples, of course, later that happened. So like the one, Emma, that you were asking about where we had the number 24, or the number 12, rather, and we said we can't break it down into 2 and 6. We would actually say the reason is because 2 and 6 are not relatively prime, but 3 and 4 are. So 3 and 4 are relatively prime. It doesn't mean either of them have to be prime. 3 and 4 is not prime, but 3 and 4, when compared to one another, are relatively prime because they have no factor in common, okay? What we're going to take a look at next is several methods for finding the greatest common divisor. Some would be taught to younger kids than older kids. Some have very nice extensions into higher level math, like high school kind of math, and some really don't. And so there's benefits and there's drawbacks to the different methods for those different reasons. And the reality is, too, that they also have places where they work for different sets of values, right? They're more conducive or more useful when you're comparing certain numbers and not comparing other numbers. So our first one, intersection of sets method. What we do is we list all the divisors of each value, and then we find the largest divisor that the values have in common. This tends to work better when the numbers are smaller, when they have fewer factors, those kinds of things, right? So if I had the number 1,000 and I had to write down all the factors of the number 1,000, that's going to be more work than I have to write down all the factors of the number 10, right? So this is kind of the idea. The nice thing about this particular method is that it's very concrete. I mean, like, you see all the numbers listed there, you're writing them all out, and then you're just finding the biggest one, right? There's no ambiguity or question that it really did what you thought it was supposed to do. Like, you can see it work. So we're going to do something with small numbers because that's actually where this is useful for. The numbers are 12 and 15. So we're going to list all of the factors of 12. And just like you've seen me do before, I prefer to list them in pairs so that I don't miss anything. So 1 and 12 would be my first ones. What would come after the number 1? 2. And 2 divides 12. So 2 and 6. What's next? 3 and 4. And then once you get to 3 and 4, there's no space between them for there to be anything else, right? And in some sense, if you sort of go around the circle or the loop that you've created, you can see all of them are there, and they're even in order. Okay, so these are the factors of 12. And then we're going to do the factors of 15. Okay, do the same thing. So I'm going to do 1 and 15. 3 and 5. There's very little space in between. There's a number 4 in between, but 4 doesn't work, so we're done. And then we're going to consider all of these numbers, right? There's 10 of them on my screen. And we're going to find the biggest number in both lists. And what is the biggest number in both lists? Happens to be the very small number of 3. So again, a greatest common divisor is first and foremost a divisor. It's not a big number because divisors have to be smaller than the values you're working with, or at least no bigger than. So my greatest common divisor here is 3. Okay? Any question on that one? It's called intersection of sets because these are sets of numbers, like I could write them in set notation. An intersection, remember, means what do they have in common? So that's what we're looking for. Method number 2 is probably the one that's most useful for continuing on in mathematics. It's one that's very commonly taught, but it sort of hides a little bit of what's going on behind the scenes. It does work much better when the numbers get bigger, though. So the first step in this method is to construct the prime factorization of each number. We did that back in section 4.2. We did it with either factor trees or that division algorithm. The second thing is to look at the factorizations that you've created for both or all 3 or whatever of your numbers. Any factors that they have in common, we're going to write down. So if they both have a number 2 in their list of factorization, 2 is going to be a factor in our common factor. If they both have a number 15, or not 15, 5 in their factorization, then 5 is going to be one of the common factors they have that we're going to write down as well. And then do you remember, it's even still on the board, this one where we had the 111 that Kaylee asked about over here? And we pulled it out and we said, how many of them are in both of those sets of numbers, right? And we wrote down the smallest number. That's the same thing we're doing on step 3. We're comparing the values and we're saying, well, this one has 7 and this one has 4, so how many do they have in common? 4. It's the smallest thing that they both have, the biggest thing that they both have, which is the smallest value of the 2. So we write that down on number 3. And then on number 4, we actually multiply it back out to find the numerical value in sort of standard notation instead of factored notation. Okay? So the problem begins in a standard notation form and it ends in a standard notation form. So we're going to see bigger numbers on the next example, right? 400 and 360, that's bigger, right? Okay. I'm going to do this with the division algorithm just to give you a little bit more experience with it. We'll start with the number 400, and remember, we want the smallest prime that goes into 400, which would be 2. And I would get 200. And then I would use 2 again, and I would get 100. And I've got 2 again to get 50. I promise the 2s will end. One more time for the 50, and I get 25. Which is not divisible by 2, but it is divisible by 5, you bet. So I have a 5 here and a 5 here. All of the factors, all the prime factors rather, are right here on the side. How many 2's are there? 4, so this is 2 to the 4th times 5 squared. Good. Okay, this is the prime factorization of 400. We did that back in section 4.2. We're going to do the same thing for the 360. We're going to divide it by 2. So I get 180. 2 again gives me 90. 2 again gives me 45. Okay, so far so good? All right. Man, it's really tempting to say 45 divides by 5. And it wouldn't be wrong. I mean, it does divide by 5. But this method wants us to go from smallest to largest. There's a number before 5 that divides it, which would be 3. So what is 45 divided by 3? Close. 15, sorry. Maybe I just heard wrong with the ambulance system outside. Ugh. And then a 15 will divide by 3 again to give me 5. So again, all the factorizations over here on the left. So this is 2 to what power? Third times 3 squared times 5. Okay, So in terms of this list of like to-do, this is a to-do list, all we've done so far is step 1. We did the prime factorization. So the second thing we're supposed to do is we're supposed to look for the prime factors, the bases that they have in common. So what numbers do you see that they have in common? 2 and 5. So my greatest common factor, or my greatest common divisor, is going to have a 2 and a 5. But the greatest common divisor here is not just 10. It's not 2 times 5. We need to figure out if there's any exponents that the 2 and the 5 need to include. So if we go back to the original problem here, this is 2 to the 4th and 2 to the 3rd. How many 2's do they have in common? They have 3 in common, right? And the reason that happens, by the way, is because what's really going on here is this. Right? That's what 2 to the 4th means. And this is what 2 cubed means. So there are 3 2's that they both have. How many 5's do they both have? They have 1 in common, right? 2 cubed is 8. 8 times 5 is 40. So the GCD of these two numbers is 40. Okay, raise your hand if you've seen this method before. Did you see that somewhere in high school? Just one of you? That's it? 2, 3. I wonder what methods you guys used. Maybe we'll keep going and see. All right, our next method is my favorite. It's actually called division by primes. And you might look at that and say, well, didn't that what I just did? I did a bit of divisions by primes, a whole bunch of them. And we did. But this specifically allows us to do the division faster. Maybe that's why I like it. What we're going to do is we're going to write the numbers in a row. And then we look at the 2 numbers that we're dealing with, or 3 or whatever. And we ask ourselves, what prime number divides all of them? Not just what prime number divides one of them. And we divide by it. And then we keep doing that over and over again until the 2 numbers no longer have anything in common. So divide the quotients by a common prime factor. Repeat step 3. And then step 5 is that the GCD is the products of the primes that we divided by. Let's take a look at the example. This one has 410 and 360. So we write the 410 and the 360 sort of beside one another. And we ask ourselves, what is the smallest prime number that divides both of them? And it is a 2. And then we do the division. This is now 205 and 180. So far, so good. Now, while 2 still divides 180, it doesn't divide the 205 any longer. So I will not divide by 2 again. So I go up the list. How about 3? Nope. 205 won't divide by 3. How about 5? 5 will do it. What's 205 divided by 5?
41.
It's 41. And 180 divided by 5 is 36. Now, again, I don't really need to test 2's and 3's anymore because I already found out that we're done with them, right? We're going in order from smallest to greatest. Are these both divisible by 5? Nope. And the reality is that if you take the square root, remember we talked about this last time on what other primes will work businesses? If I take the square root of 41 is just a number a little bit bigger than 6, between 6 and 7. So once I hit 5, and 6 is not prime anyway, you could even say maybe 7, but these don't divide by 7. Like there's nothing else that I can divide here and make it work. So the answer is actually the values that we've divided by when we multiply them back together. So the greatest common divisor is 2 times 5, or 10. I like this method because it avoids all the sort of unnecessary division that we had to do over here that didn't apply. Yes, Emily?
So could you have done how it was like 410 and then 360? Instead of dividing by 2, the
Okay, but remember, what is the method called?
Oh, by primes.
Yes. And that's why, is because we're going to divide only by primes.
Okay.
Yeah. The reality is, could you divide by 10 and get the answer the same? Yes, you could. It just doesn't fit within the method's description, that's all. Yeah. Okay, there is one other algorithm that we're going to look at today, all right, for greatest common divisors. It is definitely the one that hides behind the scenes what's going on the most. This is called the Euclidean algorithm. You know, like Euclidean geometry, the geometry you did in high school. Same guy. And here's what the Euclidean algorithm says. This is so messy to write down, but the process is not hard, okay? You divide the larger number by the smaller number, and then you divide the previous divisor by the remainder. And then it's one of those shampoo things, wash, rinse, repeat, right? You repeat. And you repeat and you repeat until you get a remainder of 0. The last number that you divide by is your GCD. Okay. Doing this is not hard. Writing it is weird. It's kind of like when we did our division test for divisibility 11s, right? Super weird to write down. But was it hard to do? No, you just added up every other number and you did some subtraction and then you divided by 11, right? I mean, it wasn't hard processing. The same's true here. You divide your bigger number by your smaller number. So the bigger number is 126 by the smaller number 72. All right, so how many times will 72 go into 126? One time, yep. And I do the 72 here and I subtract, and what's the subtraction value, the difference? $54. Yep, 54. Okay. So that's step 1. Divide the bigger number by the smaller number. Step 2 says divide the previous divisor by the remainder. So the previous divisor, the number I originally divided by was 72, and the remainder is 54. So what it's saying is to take those two values and do the division again. So the 72 is now underneath the division sign, and the 54 is on the outside. We divide the previous divisor, 72, by the remainder, 54. How many times will 54 go into 72? Once, and I subtract the 54. So what is 72 minus 54? 18. Okay, wash, rinse, repeat, right? So now I'm going to take the previous divisor, 54, divide it by the remainder, 18. How many times will 18 go into 54? 3. What's 3 times 18? 54, which gives me a remainder of 0. That 0 tells me to stop. Not only does it tell me to stop, but it also tells me I have found the answer to this question. It's the last thing I divided by. It's 18. Okay, your book goes through and talks about why this works, and that's fine. I don't think that that's something you would share with your students, even if they asked. You think you'd try to talk to them about the fact that that's probably just a little bit more math above their heads than they really need to be worried about right now. It's hiding though, right? Like, this is not at all obvious why this should work. I mean, maybe even on the last two you felt like this is a little bit convoluted, but this one's really hidden. This is the divisor though. It is greatest common divisor 18. And that's how we would finish that method. Any questions?